In the final section of this introduction to vectors, we will discuss vector multiplication. Because there are two ways to multiply two vectors. First, we have the scalar product, and then second, we have the vector product. The scalar product is also called the dot product, and that is because we denote it with a little dot. In contrast, the vector product is also called the cross product, and that is because we denote it with this little cross. And this is an important point to remember, is that whenever you see two vectors being multiplied with this little symbol, then you know we are talking about the cross product. Now, the scalar product actually takes its name from the fact that the output is a scalar, whereas the vector product, the output is a vector. Scalar product, the computation is very simple. However, for the vector product, it is a bit scarier, as you can see here. Now, this notation has a very specific meaning, and we won't really go into what it all means. I am just going to show you how to perform the computation. If you are really interested and want to do some deeper reading, then I'll just give you the hint that this is called the determinant of a 3 by 3 matrix. Okay, and we will start with the definition of the scalar product. So let's say we have two vectors, u and v, and we are taking the dot product. Then what we do is we take the x component of u and multiply that by the x component of v. And then we add the product of the y component of u and the y component of v. And that's it. That is the definition. Okay, but what does the scalar product actually mean? Well, let's take the vectors that I've drawn on screen. We have u. Now that is clearly ux I hat plus uy j hat. But remember that uy is equal to 0. Next we have v, which is vx I hat plus vy j hat. So now we take the dot product of the two. U dot v is equal to ux vx plus uy vy. But remember that uy is 0, so this cancels out. But if uy is 0, then that must mean that ux is equal to the magnitude of u. So we can replace ux with the magnitude of u. And if we remember from our fundamentals, Vx is equal to the magnitude of V multiplied by the cosine of the angle between V and the x-axis. So we replace Vx as well. And in this case, we see that the angle between V and the x-axis is the same as the angle between V and U. So the dot product of two vectors is the product of the magnitude of the two vectors and the cosine of the angle between the two. So does this always hold? If we just draw an arbitrary vector u and an arbitrary vector v, you have to remember that the direction of the axes are also arbitrary. And this always holds. And if you're not convinced, you can just practice this yourself. But now, what if we set the magnitude of u to be equal to 1? What happens then? Well, u dot v is equal to u v cosine of theta. Well, this u then falls away because it's equal to 1. And we see that we have the x component of the vector v. Or if we think about all of this, it is the component of v that lies along u. So another way of thinking about the dot product is that the dot product represents the component of one vector that lies along the second vector multiplied by the magnitude of that second vector. Okay, and we now move on to this scary cross product. This does look pretty terrifying if you're not familiar with the notation, and we are just going to go through how to perform the computation. We won't really go into what it means. The biggest thing about cross products is that they are tedious and not particularly difficult. And as long as you can spot the pattern in the computation, you will be alright. So there are 3 steps, and the first step is where we take the unit vector I, and then we concern ourselves with all the other components that are not in the same row or column as I. We open some brackets, multiply that by I hat. And what's the computation we perform? Well, we take the product of the top left and the bottom right, and from that we subtract the product of the bottom left and the top right. And that's our first step. For the second step, we add a minus sign. And let's get rid of this for a moment. And we take the second unit vector. And we take all the components that are not in the same row or the same column as that unit vector. And we perform the same thing. So we have unit vector j. We take the top left and the bottom right. We multiply them together. And then we subtract the product of the bottom left and the top right. Now we add a plus sign. Rub this out, and I'm sure that you are familiar with the pattern now. We take this unit vector and we only work with the components that are not in the same row in the same column. We take the top left, multiply that by the bottom right, u, x, v, y, and we subtract the product of the bottom left and the top right. And we fix our brackets. And that is how you perform the cross product. But let's tidy this up. So now I've tidied it up and it's all typed up and nicely shown at the top of the screen. And now we consider the vectors that I've drawn on the screen as well. Now we've got some vector u and we've got some vector v. Now I would like you to imagine that even though we have an x-axis and a y-axis drawn on the screen here, I would like you to imagine that there's another z-axis which is coming out of the screen towards you. The unit vector associated with z is k hat, and that is this one here. Now for simplicity, we will define u such that uy is 0 and uz is also equal to 0. So u purely lies along the x-axis. Now we've got the other vector v, and the x and y components have some finite value, but we'll set vz equal to 0 as well. The reason why we're doing this is that this allows us to cancel anything out in this big scary line, anything which has a uy or a uz or a vz. So that is that, and that. You see, the important thing about maths is always make your life as easy as possible. So now we are only left with that bit here, so we will write that out again, and that in our case u cross v is equal to ux vy, and that's multiplied by k hat. Now if you remember how I defined u with no y component or a z component, we find that the magnitude of u is also equal to ux. So we can perform that substitution again. If we go back to our definitions of vectors, we remember that vy, or the y component of v, is equal to the magnitude of v multiplied by the sine of the angle between the vector v and the x-axis. So we can substitute that in there, and that is the result of our cross product. But you'll notice that we still have this unit vector k. And this indicates that the result is still a vector. And in this case, where we have u and v all lying in the same plane as the screen, the resultant vector sticks out of the screen towards you. And this is a key result. And that is that the cross product of two vectors is always perpendicular to both component vectors. But there's also something interesting, and that's the direction of the resultant vector, because it has to lie along that z-axis, and I've just said it comes out of the screen. What is stopping it from going into the screen? Well, this is the right-hand rule, and this is a fun little exercise. I'm going to draw some arbitrary vector u and some vector v. So there we go, and that's u. Sure we do the arrows. Now take your right hand and extend your index finger to lie along u, and your middle finger to lie along v. And now extend your thumb. In what direction does the thumb go? But now reverse the situation and extend your index finger along v and your middle finger along u. In what direction does your thumb point now? And this indicates something very important. And that is that u cross v is not equal to v cross u. And this is something you wouldn't have encountered before in a multiplication, because you've always been used to, let's say, a multiplied by b, that being equal to b multiplied by a. But in the case of vector products, u cross v is equal to minus v cross u. Okay, so this was all the basics around vectors. I will do another video where we take some practice problems involving the dot product and the cross product. But once you have a good grasp of how these computations are performed with vectors, you'll be surprised how far you can get with physics.